This talk is on highlights from the mission on automatic code scanning and verification. The talk is called The Mechanics of Software Security, Generate and Scan. So when you usually think about a software development lifecycle or a secure software development lifecycle, you have several components. So at first you start with risk and threat modeling, like what are we up against? What are the attackers? What are the goals they want to achieve? Then you create an architecture that tries to mitigate those threats that you have identified. I'm simplifying here slightly because we want to look at the rear part of this life cycle. And this rear part, by that I mean you have an implementation and then you go to testing and you usually iterate. And what we focus on in this mission is two parts. So one is when you have code, you need to test this code. You need to run static and dynamic code analysis on it to find vulnerabilities. You fix them, you scan again. Ideally, you do this during your development lifecycle, so for every commit. So it's not like a waterfall model where in the end you find out that you pretty much screwed it up, but where you incrementally fix. But we also have a part in the mission where we say we want to generate code that we know is secure. So because when the developer doesn't write the code, but the machine writes the code, we have a higher chance of getting the code right in the first place. So these are the two aspects for today. I will talk mostly about the analysis and testing part and leave the part about secret code generation to Krishna. And this is also along the lines of the tools, because I will be talking about stuff that goes into our code scanner VASC, and Krishna will be talking mainly about CogniCrypt. And well, I mentioned this code scanner VASC. So we have very simple goals. We want to create a production grade scan engine, beat the industry, and publish great papers. What does that mean in detail? We have to tackle various challenges in static and dynamic code analysis, and I'll go through a few highlights of what we've done over the past 2 years, or 1.5 years approximately. So whenever we look at applications, they're usually also driven by data, not only by pure code. For example, if someone or some application connects to a remote server, you want to know what is that server, which TLS protocol, for instance, you use, protocol version, which cipher suites do you use. You want to run data flow analysis, which data is transferred over that connection, because that gives you an estimate of how important or how sensitive that this transmission is, or any potential vulnerability on the transmission. You need to scale analyses because you want to scale, for example, to all the apps in a Play Store if you're the store operator. And these are all things that we have been working on. The first thing I already mentioned, sensitive data extraction. You see the 2 papers on the right that we are currently preparing for submission. Here, the idea is really, even if the app is obfuscated, even if the app dynamically creates values at runtime, we want to know these values. We want to statically reconstruct them so that we can reason about the properties, the parameterizations, the communication partners of that app, and can then build a better risk profile, and can also augment the scan results so that the analyst clearly sees this is a relevant finding and this is a finding that is technically correct, but I do not need to fix immediately. You want to know when you tell your developers we need to fix our application, is this something we need to do today, or can it also be done, for example, in the next maintenance release? And for that, it is very important to get values, to get parameterization. The next thing I mentioned is scalability. If you want to run analyses on a large number of applications, if you want to scale analyses to a large number of applications, you have to make sure that it doesn't take forever and that it doesn't eat up too much memory. So with classical IFDS-based analyses, we come from a world where a single analysis can take 150 gigabytes, 200 gigabytes of memory. This is okay if you have one application to scan. But if you're, let's say, Google, and you want to scan all applications that are freshly uploaded to the Play Store, which are like hundreds and thousands a day, keep in mind that we're also tackling updates, not only totally fresh applications, then 150 gigabytes per application is just not okay. because this requires huge amounts of memory. This requires hardware. It just doesn't scale that much. And we have managed to cut down the memory consumption of this highly precise data flow analysis by about 60 to 80%, depending on the application. So this is clearly research on making analyses practical for the real world, making them scale, not just in a single application scenario, without losing precision, of course. You see the paper on the right. It is currently under submission. I'm pretty sure it'll get accepted. Speaking of massive scaling again, so we talked about static data flow analysis, scaling a static analyzer, but some things are better to be analyzed in a dynamic environment. So you run the application and you observe it at runtime and see what it actually does. In that case, you have the problem if you have one phone, for example, to analyze Android apps, you can run one application, because usually the application has activities, has things that are displayed to the user, and if you put it to the background, it usually changes behavior. So one phone, one application. But now the problem is, if you want to analyze many applications and you want to run it for, let's say, 2 or 5 minutes per application, then you need a lot of time if you have a lot of apps. The other option you can go by is just have a lot of phones. But this is not as easy as it sounds, because the technical challenges behind scaling dynamic analyses over a broad variety of phones, starting from how do you power those phones, how do you distribute apps among those phones, how do you get even somewhat reproducible results, because phones tend to change behavior if a battery gets low and things like that. This is actually a challenge, and this paper you see here has been accepted at MobileSoft this year. So there's always the papers for that topic on the right side. And one final research direction I would like to mention is we have worked on automatic app categorization. So the idea is, if you have an app collection and you want to know what can I expect from this application, what would be kind of expectable behavior, then you need to know in what category this application would normally fall, because you would expect something different from a banking app than you would, for example, expect from a gambling app. And the categories that developers put their apps in something like the Play Store, they are not always correct. Some developers just get it wrong, and some deliberately put applications into the wrong category to fool users. And this is why we create a machine learning based approach to create an automatic categorization. And the paper on the right side, we're currently working on a resubmission of that paper, and I think we will get it published next year. Now, I have shown you quite a few things we have done research-wise. And what do you do if you've got a lot of algorithms, a lot of implementations, a lot of great tools and techniques? You build them together. And this is this VASC scan tool that you see on the right side. That's just a screenshot. This is a static analysis tool. You just drag and drop a binary application onto that scanner. It doesn't really matter whether it's an iOS application, an Android application, a Java web application. We support like tons of different formats. And then all these algorithms you have seen and many more are run, and they give you vulnerabilities inside these applications. Currently, you get your list of vulnerabilities. And now in the second half of the mission, we'll be turning more towards verifying these vulnerabilities. So you plug in a phone and you get a result of whether we could trigger this vulnerability automatically or not. Because now we also have the dynamic infrastructure, things like the scaling of dynamic analyses, that we're able to tackle this next step. And just in a couple of seconds, we also, as kind of a community service, analyzed the German Corona Warn app. We did security testing on the app implementation and created a few issues on GitHub in the official issue tracker. We created a comprehensive threat model for it, and we're now running a social acceptance analysis, which will also result in a paper together with TU Darmstadt. and this is ongoing research work. Okay, and now I'll hand over to Krishna for the second part of the talk, which will be about secure code generation and verification using CogniCrypt. Thank you.
You're still on mute, Krishna.
I will talk about one other of our security scanners, aka CogniCrypt, right? So I'll try to summarize on a high level in the remaining 5 minutes what we have done with CogniCrypt and what we plan to do with it, and yeah, also what CogniCrypt does, right? So, okay, in order to first understand what CogniCrypt does, it's also important to understand the perspective difference. As Steven has already mentioned, CogniCrypt is not a traditional security scanner in the sense it analyzes your app or things like this. It helps the developers. So a brief overview of how traditional security scanners help and where CogniCrypt comes in, right? So which is helping other software developers. So currently the scenario is, let's say a developer wants to protect his data, protect his program. He would have to use APIs, which are in turn designed by these crypto experts who work in tandem with these API designers, who provide you a nice, cool interface with which the developer can secure his data. And then he develops an app, and then he runs 6 code scanners or app scanners, including WUSC. And then after he looks at the vulnerabilities, he addresses whichever ones are a priority to him, and then he distributes it to the end user. But there is an important challenge that CogniCrypt acknowledges, which is that software developers also need help well in advance during their implementation time and not just after they've built their app, right? So for that, CogniCrypt, so the core of CogniCrypt is the acknowledgement of this very important difference between software developers and crypto experts, that they need not be the same people. Of course, as I mentioned before, cryptographic experts work in tandem with API designers to give you these very nice APIs. But previous research has shown that APIs are notoriously hard to use, and they are they're not poorly documented, but they are rather complexly documented, so to say. And so it has been shown that using our previous research at TU Darmstadt, that software developers struggle a lot with using these APIs, especially crypto APIs. And as you can imagine, abusing a crypto API can have disastrous consequences. So that's what CogniCrypt tries to address. So how does CogniCrypt help the developer is that it first enters the development cycle, in the sense, as a developer, you only need to install CogniCrypt as a plugin. Currently, it's there in Eclipse, and work is ongoing for bringing it to other IDEs. And once he or she has installed the plugin into their favorite IDE, they have all kinds of support to help them in not misusing the cryptographic APIs. So what does the CogniCrypt plugin itself provide? It has 2 main aspects. One is the code analysis aspect, which we already seen in some fashion till now. Essentially, what the code analysis aspect does is the developer, as usual, once he's installed the plugin, he just goes ahead, writes his code, performs his cryptographic task using these APIs. And whenever he, let's say, abuses the API, whenever he instantiates a cipher with insecure key length, or for example, things like this, right? He would get a warning or an error based on the severity of the error, and then he'll also get pointers on how to fix them. But this is not all. Sometimes developers are not always working on legacy code. They might have to create their own cryptographic tasks for new software, for example. And currently, of course, developers' first go-to would be Google or Stack Overflow. So yeah, so it's research has also shown that Stack Overflow, almost the first instance you get or solution you get in Stack Overflow has been shown to be insecure for basic tasks like encryption. So for that, CogniCrypt also provides a code generation aspect where the developers ask some basic questions, and he answers them, and he gets the template usage. So this is all what CogniCrypt does, and of course it's easy to see that further development is required for such a promising endeavor. So we are planning to expand it to further libraries, not just JCA. We are planning to expand it to further languages, and there are scenarios like when the API's versioning disables or nullifies the previous security standards. We are also addressing that, and beyond just development, we are also working on actively growing the community by by having a community that tackles the issues that are there in the tracker, having workshops around it. And we also have a professional setup where we have releases on I think on a monthly basis now. We are planning to work on it much more frequently. And then we also have a pretty high standard continuous integration. So that's it.